Hi, my name is Ryan Kinnear. I'm going to be talking about the paper Real-Time Bidding for Time-Constrained Impression Contracts in First and Second Price Auctions. Okay, so I'm going to just give a quick introduction, some background, define the problem, talk about one of the key results on convexity, and show some simulation examples, and finally give my conclusion. Okay, so the paper is about real-time bidding, which is a mechanism to allocate advertising space on the internet. So the basic setup is that you have some user who opens up a web page or an app, and then the publisher of that web page or app, they have some space set aside in the screen to show ads to the user, which is how they monetize the content. So the user gets to use this product for free, and the advertiser pays for it by showing them ads. So when a user visits the website, the publisher takes whatever information they have about that user, sends it to what's called a supply-side platform, or SSP, which in turn interfaces with an ad exchange who runs an auction. So in this auction, the items which are for sale are basically the impressions or the eyeballs of the user here, and the bidders in the auction are demand-side platforms, DSPs, who operate on behalf of some advertisers. So the advertisers specify what sorts of users they want to target with their message, and then the DSP takes that information and figures out how to bid in the ad exchange on their behalf. So in the paper, we're talking essentially about problems faced by this DSP here. So formally, we're going to have a heterogeneous collection of items. There's going to be capital M item types, and J will define or denote a particular type of item. So the item type is like characteristics of the user. You can also think more generically. You just have some arbitrary items which are being sold at an auction. The items arrive one by one, and they have instantaneous arrival rates lambda j of t. So at time t, instantaneously at that moment, this is the rate at which of type j items are arriving at. The price of the items are determined by basically the distribution of competing bidders, and we model, so here by distribution of competing bidders I mean what the other bidders in the auction are willing to pay, and we model their willingness to pay by a supply curve, which will be denoted by W. So Wj is more or less a unnormalized cumulative distribution function, which tells you instantaneously at time t what is the expected rate of items that you will win if you bid X. So by bidding X on every item of type J, you expect to win instantaneously at time t Wj x of t items per second. And then the cost is similarly the cost of bidding X on every item of type J. And this depends on the auction, which is usually either a first or second price auction. So intuitively, you can think of Wj x of t as being the product of the rate of arrivals with some cumulative distribution function W, where Wj is telling you what is the probability to win type J given a bid of X. But it doesn't have to take this form. It can just be some arbitrary time-dependent function. So to give a kind of a picture of this, this is a cumulative distribution functions or supply curves estimated from real bidding data. So this is when time is fixed. So orange is one fixed time, 9 in the morning, and blue is another fixed time, 12 midnight. And basically this just gives a cumulative distribution function. So this has been normalized, but actually I let W be unnormalized because it takes into account the rate at which items are arriving. And similarly, we can fix X and consider their time dependence with T. So there's kind of a natural time dependence which comes from the day-night cycle of people visiting websites. So if you bid the same amount, then the rate at which you win will still fluctuate with time. And this is why we consider this time dependence. Okay, so let's talk about the contract management problem. So just to kind of set the stage here, we need some cost functions. So there's two auctions to consider. In both cases, the highest bidder will win the item, but in a first price auction, they pay what they bid, and in a second price auction, they pay the second highest bid. So for a first price auction, the cost function is quite intuitive. It's just the bid times the probability of winning. That's quite natural. In a second price auction, it's a little bit more complicated, but it's basically the expectation of the highest competing bid, which here I'm denoting by B, multiplied by the event that you win the item. And this just has this integral representation. It's kind of like a truncation of the integral for an expected value. Okay, so this is basically the first and second price cost functions. We can look at these fj functions here. So this is an example, again, from real data for a second price auction. you can see from here, and similarly the supply curves, there's not really much structure in these functions other than that they're just monotone functions. So basically you have some monotone cost functions and these monotone W functions, and from there we're going to formulate an optimization problem. So the DSP, who is acting on behalf of advertisers, they're subject to what I'm referring to as contracts. So a contract, of which there will be capital N of them, and I will denote a contract, the DSP is required to obtain CI items of some specified types, which is defined by AI by a time deadline TI. Okay, so CI is the number of contracts, or sorry, the number of items needed to satisfy contract I. TI is the time deadline, and AI, which is a subset of all the available item types, is the targeting set. So winning items of a type contained in the targeting set contributes towards fulfilling the contract. So the goal is to fulfill the contract by obtaining CI items of the types in the targeting set by the time TI, and of course the DSP, they're under an obligation to fulfill these, so they want to do so at minimum cost. Okay, so basically there's a couple questions that the DSP has to answer. So first, they need to choose what to bid on the item, and they need to choose where to allocate it. So we think about a fluid limit for this problem. So gamma is going to encode the choice of where to allocate the item, that is to which contract. So gamma ij is the rate or the probability of allocating an item of type j if it is 1 towards contract I. This is one of the decision variables, and it tells you where you're allocating the item, to which contract is it satisfying. And xij is what you will bid on an item of type j if it is going to be allocated to contract I. So this is the cost, it's just the sum of all of the f cost functions across the different types, and these constraints specify that the contract has to be fulfilled. So gamma has to be just a proportion, it's a probability distribution at each time t, and here specifies that you have to obtain the CI items of the correct types by the time deadline ti. Okay, so this is the problem we have to solve. Clearly this problem is completely intractable as it's written. F and W are just arbitrary monotone functions. There's no special structure inherent in this formulation of the problem. So to kind of illustrate with a picture what's going on here, so there's items arriving here at the rate lambda. There's m different types of items. The DSP will submit particular bids, x. They incur some costs defined by f. Some of the items are lost by not winning them, so competing bidders get them, and some of the items are won, and they're won at the rate defined by w. Once you win the item, you have to choose by picking these gamma variables to which contracts you want to fulfill them. So AI, the targeting set, defines where you can send an item of type j, and gamma tells you, or well, the DSP chooses gamma to decide where to send them. So you can think of each contract as kind of like a bucket, and they need to fill this up with the correct type of items by the time deadline. So this is a kind of a picture of how this works. Okay, now we're going to talk about how to actually solve this problem. So as I said, problem P, as it stated, is intractable, but there's a remarkable transformation of variables which transforms the problem into a convex program. So rather than choosing the bid x, we instead choose what is the target rate of supply, which I'll denote by S, which we want to win. So in order to win S supply, we bid W inverse of X. That's the bid that you need to submit on every item in order to win S supply. So this W function is time and type dependent. I've just omitted those from the notation to make it look simpler. So of course, because W is a strictly monotone function, it's a cumulative distribution function, you can choose X or S. They're both it's both completely equivalent because you just have this invertible transformation between them. And now I refer to this lambda function as the acquisition cost, and lambda is just the cost of winning items at this rate S. So W inverse of S is what you need to bid in order to win S items, and F is the cost of placing that bid. So F composed with W inverse gives you the cost, which I refer to as the acquisition cost, of winning items at the rate S. So here's just some quick calculations to show that this is convex. Basically, in the second price case, lambda is equal to the integral of the quantile function of W, and because W is monotone, the derivative of this is monotone, and therefore it's convex. So to give another example here, so if you remember, these f and w functions just had this arbitrary monotone character. There was no special structure. But here, this lambda function, once we do this composition, is this nice looking convex function of the target supply S. Okay, so here's pretty much the main theorems. So in a second price auction, if W is continuous and strictly monotone increasing, then the acquisition cost function is convex. In the first price case, it's a little bit more complicated. You need this extra condition that W is too concave. The distinction between too concavity and log concavity is not particularly important. Essentially, you could think of the sufficient condition that if W is log concave, then the acquisition cost function is convex in the first price case as well. So there's almost no conditions required in the second price case, and the first price case you just need this log concavity. You may be aware that most kind of famous cumulative distribution functions happen to be log concave, so I think that this condition is fairly weak. And then once you have this theorem that these acquisition cost functions are convex, by that transformation of variables that I described earlier, where you optimize the rate of winning rather than the bid itself, you transform the original problem P into this convex problem here. So now S is the rate at which you win items, and there's a cost associated to winning that many items, which is given here. And then this now encodes the contract constraints. So R is the rate at which you allocate items of type J towards contract I. So you're choosing this rate, and now you just have this linear constraint, which tells you that over the course of Ti time, you have to have allocated Ci items of admissible types given in AI towards contract I. And then here just normalizes things. So if a solution to this exists, then you can construct a solution to the original problem. That is, you can find the optimum bids and the optimum allocation gamma. Now notice here, it's part of the theorem that the optimum bid does not depend on the contract. The optimum bid depends only on the type of item. Okay, so the convex program I just described is analogous to a transportation production problem. So the sink nodes are the contracts, and the production nodes are the given by the acquisition cost functions. So you have some production nodes here. You choose how much to produce at these production nodes, which is given by S. And once you've done that, then you have some transportation network, where this network is defined by the admissible types A. And then you just solve a transportation problem on this network. Okay, so it's analogous to a transportation production problem, and it's convex. Okay, so now let's look at some practical results. So to actually solve the problem, in the second price case, it can be reduced essentially to a sort of static time independent case. In the first price auction, that's not true. But if you do this discretization, this is kind of an acceptable computational method for solving the problem. So the problem is in general time dependent. The DSP kind of wants to forecast forward in time how much supply will be available, and so we do this discretization in time to construct this convex optimization problem. Now this is a finite problem. There's surely much better algorithms than just this discretization, and that's kind of a topic that I'm working on now. But this is, a fairly reasonable first pass at this problem. We just discretize in time and solve this finite convex programming problem. As well, this has some kind of nice properties. Because the constraints are all linear, solutions of this problem are feasible for the original problem, and basically by looking at the particular way we discretize this integration, we can show that the quality or the solution kind of converges at the rate 1 over k, where capital K is the number of discretization points. Okay, now in reality, the environment in which you're bidding is not just this nice deterministic fluid limit, but rather it's stochastic. So I looked at a couple of kind of natural heuristics for this to deal with this stochasticity. So if we let little ci of t be the amount of supply acquired for contract I by time t, then we can apply a receding horizon. So basically just you construct new contracts with time deadlines that are the original deadline less the current time, and have a target supply of the original supply less the already attained supply, and then you just solve the problem again. So this is called like the resolving heuristic or model predictive control, receding horizon, things like that. You're essentially just resolving the problem as if it's deterministic multiple times over the lifetime of the contracts. And then similarly, we can overinflate the target supply. So instead of aiming to obtain Ci supply, we aim to obtain 1 plus delta Ci. Now this delta becomes a parameter. And there's kind of some justification for doing this over fulfillment or over targeting, which is that if you have some probabilistically constrained optimization problem where you want to optimize subject to the probability that you fulfill the contract, then this optimization problem with the probabilistic constraints can be approximated by, or is in fact equivalent to, a problem where you just inflate the target supply. Okay, so here's a kind of a one-dimensional simple example here where the expected amount of or the forecasted amount of supply is given by the dotted line, but the actual supply is this red line which drifts downwards, and the receding horizon and the over-provisioning kind of smooth out the acquisition to ensure that the contract is actually fulfilled and without spending too much to do so. And here's some simulations with real data. So on the bottom here's that adjustment parameter delta. The blue is where there's no receding horizon, and the orange is where there is. So without any supply overinflation, without a receding horizon, then a large proportion of the contracts are not actually fulfilled. But by adding a receding horizon, almost like 95 or 97% of the contracts become fulfilled in this simulation. And if you increase the delta parameter just a little bit, then you can get almost all of the contracts to be fulfilled. And then similarly, the receding horizon kind of helps you control the costs. So of course the lowest cost method has no receding horizon and no adjustment parameter, but this doesn't actually succeed in fulfilling the constraints. But when we add some overfulfillment and also a receding horizon, we kind of control the costs and fulfill the contracts with a much higher probability. Okay, so that's essentially the paper. I consider the key insight to this whole thing to be this convexity. So I think that this convex transformation can apply to a lot of different optimum bidding problems. And essentially, this contract management problem is just equivalent to some convex transportation production problem. That's the paper. Thanks.